तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we have been looking at computing the Fourier transform of a function using some numerical methods, and we looked two methods we looked at are discrete Fourier transform and the fast Fourier transform. So that is, if you have the function values tabulated at certain points, and then how do we compute the Fourier transform? So that was a problem, and we looked at the first method we looked at was discrete Fourier transform. So today what we do is we will actually look at the implementation of these techniques, that is fast Fourier transform and the discrete Fourier transform for a set of values, for a set of function values which we know of. That is, we know the functional form, and so hence we know the Fourier transform, how it should look like, and then we can compute them using this numerical techniques which we looked at in the last class. The first thing is the discrete Fourier transform. So as you we might remember that the idea here was to have the function values being tabulated at n equal intervals. Okay, so we have the function values tabulated at n equal intervals, and we call them as f0, f1, f2, etc. And let's take case 8 such function, that we have tabulated them at 8 points. So we have f3, f4, f5, f6 and f7. So we have the function values tabulated at this 8 points, and you want to compute the Fourier transform of this. So these are tabulated at equal intervals. So we said that delta x, the distance between, so let's say this f of x now we are tabulating. So f of delta x is now t, the whole time interval, whatever the interval which is between these two is, divided by n. So let's say L divided by n in the case of spatial variable. Okay, so we divide this to n, where n is now 8 here. Okay, and then we have this tabulated function values. So the notation we were using was that this f0 will be now written as f subscript 0, and this is as f1, f2, f3, f4. So we use this notation fn as the function value at n, at n point. Okay, so that's the notation which we are using. Okay, so we see that here. So we divide the total interval into n equal intervals and denote this function by fn. That's what we looked at, and then we want to compute the Fourier transform as that. If you remember, the Fourier transform which you are going to compute is computed with this expression, right? So the idea, you remember, was that we want to actually compute the transform, and then we have so if you know that the discrete Fourier transform can be written in this as f k. We normally write it as sigma e to the power of so we say f of x, right? F of k is f of x e to the power of minus I k x. Okay, that's what we will do, right? For all x values, discrete values of x, we would sum over all x values. Okay, so whatever the limit are. Okay, that's what the actual discrete form is. Now, but now we have replaced the x. The x is now replaced by, so now we are going to write x as some delta x times n. Okay, so that's our x. Okay, and similarly our k value is actually 2 pi divided by whatever be the interval is. Let's say t is the total interval, okay, and then this total interval multiplied by some m is our km. Okay, so we have an xn. Okay, so we are going to replace this continuous variable x by a discrete variable xn, which is delta x into n, and km by the smallest k vector which we can get, which is 2 pi by the total interval divided by multiplied by some number, an integer m. So we have these two discrete values, and that's what we are going to substitute there. So now when you substitute that in this, we get the expression which I just now written. So we say that fk is now become sigma fn. Okay, so that's our function value at xn into e to the power of we say minus I omega 0, we said m times n. Okay, so now omega 0 is this value, okay, and omega 0 times n. That's what we are going to. So that's the expression which you are going to write. Okay, and now this sum goes from n equal to 0 to n minus 1, where n is so n is a total number of points. So if it's 8, this goes from 0 to 7. That's the sum which we are going to write. Okay, so that's basically the sum which we want to compute. Okay, now let's try to use this function here and this form of this expression for the discrete Fourier transform first, and compute the Fourier transform of a function of this form. That's a Gaussian. Okay, let's take a Gaussian. So we have a function of this form. Okay, so now I'm going to write, I have a function which is of this form. Okay, so that's my f of x, and this is x. Okay, it goes from in our specific example we take it from -1 to +1. Okay, so it goes to 0 by that, almost to 0 by that time, and this actually the function form which I am going to use in the program is e to the power of -5 times x squared. Okay, so I know what the Fourier transform of that is. Okay, so this will be the Fourier transform of this would be some factor which is a normalizing factor multiplied by e to the power of minus k square by 20. So because the Fourier transform of e to the power of minus a x squared is, so the Fourier transform of that is with some, I write proportional here because there is some constant, times e to the power of minus k squared by 4 times 5. That's what you would get. Okay. So so the Fourier transform of e to the power of minus a x squared is given by up to a constant factor is given by e to the power of minus k squared by 20. Okay, that's what we should get. Okay, so so we know the form of that, so we can compute this using the discrete Fourier transform. Okay, that's what our aim would be here. So let's take this function and let's discretize this into a certain number of points like this. Okay, so one is this, and then some equal intervals we will discretize this, okay, function, and then we will call them as f of 0, f1, f2, etc. So care should be taken that we are going to call this as f0, f1, f2, f3, f4, f5, f6 and f7 like that. Okay, so because of that my f0 value, so x0 value should be -1, okay, not 0. Okay, so I should add xn as delta x times n then minus my total interval divided by 2. Okay, that's the xn I should actually substitute here. Okay, and then this would be now L is 2, the total interval. Okay, so now that would be my form. Okay, so my xn interval xn is given by delta x times n minus L by 2 because I start from here. So L is this total interval L, which is equal to 2. Okay, so now that's what I have. Okay, and then so if I do this, okay, this form which is given here normally in any textbook which you look at for the discrete Fourier transform, what you see is this. Okay, now that gets modified a little bit. Okay, now that will get an e to the power of an additional term, e to the power of minus I pi to the power k. Okay, so you will find this. This should be k here. K is the integer. Okay, so you will get an extra factor here. Okay, which is multiplying this. That means it would change the sign of all the odd k values. So that's something which you should be careful about. That is, if you are going for symmetric interval, and then this xn is actually having an additional factor here, which would show up in the Fourier transform, in the discrete Fourier transform, by this quantity, which you can see by substituting this into this expression straight away. So actually what we would be computing is this quantity. Okay, just to get that correct, and that's our program which you will look at now. So we look at a program which implements this. Okay, so here is the program. Okay, so this program is it's a discrete Fourier transform. Okay, so in this I am reading off I have a file called real data, which is actually the data which contains this function. Okay, so we can actually plot that and then see first. So we have so we'll plot this using okay, so here is my plot of this function. Okay, I guess you could see this that I have a Gaussian function here, which I have discretized at 1, 2, 3, 4, 5, 6, 7, 8 points. Okay, so I have the 8 points. This is Gaussian when discretized. I will use a different symbol for you to see it better. Okay, so here you can see it better. So that's here is my Gaussian function, which has been now discretized at 8 points. Okay, so now that's the function which we are going to use to compute the this is the Fourier transform of this is what we are going to compute using the discrete Fourier transform. So let's look at that. Here, so that this real data contains that 8 data points. So I have 8 data points. So n, that's 0 to 7. So I put n equal to 7 here. That the value goes from 0 to 7. Okay, so starting from 0 to 7, it will read off that x and f values. Actually, as you see that when you compute the discrete Fourier transform, actually what the x values for which this function is evaluated, that information is not here. Okay, so that's what I'm warning you about this one. Okay, so when you look at a standard textbook and see this formula here, we don't have the information about where the x values are. As long as it is equally spaced, okay, this function should work. Okay, but to get this signs correct, the signs correct, the sign of the Fourier terms, the Fourier transform correct, we need to also multiply it by e to the power of minus I pi by k, but depending upon what your interval actually is, where you start from this. Okay, of course you don't have to do this if your origin was here. Okay, that is, if this whole thing is shifted, then you don't have to use that. Okay, there is a shifting factor there, which you have to be careful about. Okay, so now you have the function you read off here. Okay, so we'll read the function values into this. We are going to use only the f. We are not going to use this x values at all. Okay, we are going to use only the f values here. Okay, so now this is our what I called in this thing as k. Okay, my basic omega naught. Okay, so that is 2 pi by n plus 1. Capital N is n plus 1 here. Capital N is 8. Okay, so I'm reading from 0 to 7. So n is 7. So but number of points is 8. So that the smallest k value, the smallest wave vector, the smallest vector k value I have is 2 pi by n plus 1. That's 2 pi by 8. That's my omega naught. Okay, so then for each of this k values, so now I substitute, I find this transform. Okay, so now we look at this here again, that I want to find this sum. So now to find this sum, this is a complex number. Okay, so now many of the languages like C does not handle complex numbers. So, I split this into 2 and I would write this as sigma n equal to 0 to n minus 1. I would say f n. Now, this will be written as cos and sine. So, okay, I will write it as cos of I omega naught. So, cos of omega naught k n plus pi k. That is what I would have. Okay, and then that is first term. Okay, and then I will say that is plus I times minus I times sine of omega naught k n plus pi k. Okay, so that is the sum. Okay, so now I split this into 2, okay, so that I can evaluate this term and this term. So that is the imaginary part and that is the real part. So I do the real part and the imaginary part separately here. Okay, so I times okay, I will do that. So I have the imaginary part and the real part and the imaginary part separately. Okay, so that is what I have in this program here. Okay, so I have the real part here, okay, and which is cos of the omega naught multiplied by the j and I here. So I is the k values. Okay, so I is the one which multiplies the pi also. That's my k on the board. What I have written. This is k. Okay, and this is the j value is the n. Okay, in which I sum over. So j value goes over. So function is evaluated at different j values. Okay, and we sum over all j values. That is 0 to n. 0 to n, little n, which is 7. Okay, 0 to 7 in this case. So I sum over all that. Okay, initialize the sums and for the real and the imaginary part. Okay, and I do this sum. So then I have the Fourier transform. Okay, so now I can do this sum explicitly, and I would get the Fourier transform for each of this I values up to n plus 1 by 2. That is what I am doing. Okay, so I take the first 4 k values. Okay, so that is n is 7, so n plus 1 by 2 is 4. So I get the first 4 k values here, okay, 5 k values, and that what I am going to print out into this file, okay, which is called which I call as dt underscore data. So the discrete transform data, I am going to put that. I am going to into that file. I am going to write the function values, the real part, which is sum, the real part, and sum 1, which is the imaginary part. Okay, so I will write these two into this function, into this file. Okay, and I will also write the k value. Now the k value is pi times I. So that is my k value which I have. So I will write that also. Okay, but remember the smallest k value in the real units, the smallest k value is 2 pi by this distance. Right. So that is the smallest k value I have. So 2 pi by that distance is 2. Okay, the smallest k value is actually k the k small. The smallest k value is actually 2 pi by 2. So that is pi, right. So that is what I am trying. And then pi multiplied by the integer multiples of that pi are the other k values. So I am writing that here. Okay. So I have the different k values, and the real part corresponds to the Fourier transform and the imaginary part of the Fourier transform. That is what we have. Okay. So now this file, I will plot this file now. So now this file is I called dt data. Right. So again we will use the same symbol. Okay, so now that is the Fourier transform. So I have done only one part of the thing. It is symmetric. So as I said, the Fourier transform of the Gaussian is a Gaussian. Okay, so now it is symmetric. Okay, so I plot only one part of that Fourier transform. Okay, now it starts from 0 to 12 here. Okay, so this is one part of the Fourier transform, and the other part is symmetric. So I didn't compute that. So that is why I said only the first 5 of the Fourier transform which we have computed here. So now we see that this is a pretty good Gaussian, and it actually fits in with exponential minus k squared by 20. Okay, it actually fits into that. I can show you that here. Okay, so you can see that it fits in very well through that curve. Okay, I'll just increase the line width a bit. Okay, so you can see this function. This is the actual the function. This green curve here is a function which I have got if I had done the Fourier transform analytically, and I did an 8-point discrete Fourier transform. Okay, and I get numbers which are pretty good. You can see that they actually go almost onto this into this line. Okay, and considering the fact that we had only used 8 points to compute this, this is a reasonably good result. Okay, so that's a discrete Fourier transform implementation. Very simple to implement. Okay, but we, as I said in the last class, this requires n to the power of 2 operations. So it's not computationally very efficient. So we need n squared complex operations. So instead of this n squared complex operation, we have done 2 times n square real operations by splitting this Fourier transform here into two different, that is a cosine and a sine transform. And in our calculation here, the imaginary part of this is 0 in this particular function. So we see that this is easy to implement, and we can compute and we can obtain a reasonably good accuracy. So now we look at the fast Fourier transform implementation. As we said in the last class, that this fast Fourier transform technique reduces the number of operations to n log n. So hence it is the most popular, the most used method for computing discrete Fourier transforms. So what was the technique? The technique was that we would have the function values listed like this, right? And then we would split them into 2 halves, okay? And then take the sum between these 2, right? And then replace this function by the sum, and take the difference between these 2 and replace this function by the difference multiplied by w to the power 2, w being e to the power of minus I omega naught, where omega naught is the same as what we just wrote now, 2 pi by n. Okay, so that was a technique. Okay, so we just briefly go through that. So we write the Fourier transform, in this case the discrete Fourier transform, as now fn w to the power n k. That's what we write. Okay, and then this w here is e to the power exponential minus I 2 pi by capital N. Okay, where n is the number of points. So that is exact. This is the same as what we used in the discrete Fourier transform case. So we use this. Okay, and then we just write that into 2 halves. Okay, so it's n equal to 0 to n by 2 minus 1, and n starting from n by 2 to n minus 1. That's what I just now said. We split this whole interval into 2 intervals, okay, and write this as 2 different sums. Okay, and then we notice that I can change a variable here and then make the interval, the range of the sum the same. Okay, so I will replace this n by m minus n by 2, okay, and then write the sum as m equal to 0, n equal to 0 to n by 2, and m equal to 0 to n by 2 minus 1. Okay, where here now f instead of n, here now it is f m plus n by 2. Okay, that's the difference. Okay, and now we have 2 pi by n times k instead of n is n m plus n by 2. We have to change a variable here. Okay, so instead of the sum going from n equal to n by 2 to n minus 1, we have made it to go from 0 to n by 2 minus 1, so that these 2 limits of the sum are the same. And now I can combine these 2 and write it in this fashion. Okay, and then I say that if I can write the Fourier transform, the discrete Fourier transform, now as fn plus e to the power of minus I pi k fn plus n by 2 e to the power of minus I 2 pi k n by n, and that is our omega naught. 2 pi by n is our omega naught, and e to the power of I omega naught is w. So this part is actually w to the power k n. That is what we see. Okay, so now we notice that this is simply means that for all the odd case, this is a plus sign. Okay, for it's a minus sign. Okay, this is for odd k it's a minus sign, for an even k it's a plus sign. So we can separate out the odd and even sums. Okay, that is the key observation for the implementation of for fast Fourier transform. So, this odd and even k's can be separated here. Okay, that is what we do. Okay, and then we will write for the even function as plus, right? Even function now it's plus. So, now k is replaced by 2k, okay, such that k goes from 0 to n by 2, and then we have only the even values computed here, and the even values it's plus because e to the power of I 2 pi k is minus 1 to the power k, and it is 1 plus 1 for even k. And for odd k values we know that it is minus sign here, right. So, because e to the power of I pi k is a minus, it is negative for an even or for odd function, odd values of k. Okay. So, we have the even and odd separated out. Okay. So, let us write that here, and that is what we are going to use in the program now. Okay. So, and we will do that for the same function again. Okay. So, we are going to write this now as f0 minus f1 and f0 minus f4, and here we are going to write f0 plus f4, f0 minus f4 into w0, and here we are going to write f1 plus f2 f5, and we are going to write here f1 minus f5 w1, and here f2 plus sorry, I made a mistake, here it is f0 minus f4 into w0, and here it is f1 plus f5 into w1, and then here we have f2 plus f6, and here we have f2 plus f6 w squared, and here we have f2 minus f2 plus f3 plus f7, and here we have f3 minus f7 times w cube. Well, that is what we have. All the differences, the difference between the functions multiplied by the weights, okay, where w remember is e to the power of minus I 2 pi by n. Okay, that is w. Okay, so n is a total number of points. So then this is the Fourier transform of the. This is the first step of this thing, and then we take this, we call this as G0, G1, G2 and G3, and we call this as H0, H1, H2 and H3. That is what we did, and then we continue this process again. So now we did this, and we said that here I will replace by G0 plus G2, and this I will replace by G1 plus G3, and this is G0 minus G2 multiplied by w power 0, and this is G0 G1 minus G3 multiplied by w to power 2. Notice that it is 2, and here it is H0 plus H1, and here so H0 plus H3 H2, and here is H1 plus H3, and this is H0 minus H2 w power 0, and here H1 minus H3 w power 2. We can do one more step, right? We can take the difference between now we have these quantities. Now we can take the, so we have divided this here 4 into 2, and now this became 4. We have 4 divisions. Okay, 4 sets. Okay, now we can divide this further here and take the sum and difference and write that again. That is the key way of doing the discrete Fourier transform. So at the end of it, we have the Fourier transforms listed here. Okay, so that is the observation. Okay, so we have f2k, and then we continue this and writing it as discrete Fourier transform, and that is what we did. Okay, so let us write it here in this fashion. So we start from here. We want to take this as 2 sets. Okay. So you look at that, each step I go forward, I divide the interval into 2 to the power of that step intervals. Okay, so first step I do 2 to the power of 1, right, interval. Okay, so I have the whole set divided into 2 to the power of 1 interval, that is 2 intervals. Okay, and the next step I have 2 to the power of 2 intervals, that is 4 intervals, that is 1, 2, 3 and 4. Okay, and the next step I should have to do 2 to the power of 3, that is 8. Okay, that I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I will be 8 intervals, and that is the end because I have only 8 points. Okay, So that means that the number of points to start with should be a power of 2, okay, otherwise I can't do this. Okay, now that's a restriction we have with fast Fourier transforms. So the number of points we start with should be always a power of 2. Okay, so in this case we have taken 2 to the power of 3. Okay, so it's a restriction on this. Okay, so now if you do this now if you take the sum and difference between these two functions, okay, and that will give us, so that's the sum and difference, the sum between these two will give us f0, okay, and the difference between these two will give us f4, etc. Okay, so that's what it is. And we also saw that what we get at the end is a jumbled up version of what we started from here. Okay, now the f0 will be replaced by the Fourier transform k equal to 0, but f1 will be replaced by the Fourier transform f for k equal to 4. Okay, but f2 will be replaced by the Fourier transform for f equal to 2. So that is f0, and that will be f4, and that will be f2, and this will be f6. Okay, so that's how it goes. Okay, so f3 will now be replaced by f6, etc. So the way to see is the following: that I have the function values written in this order. Okay, now this is in the binary. Okay, that's 0, 1. This is the least significant bit, and that's the most significant bit. So I start with the 0, 1. This is 2, and that's 2 plus 1, 3, and this is 0 plus 0 plus 2 to the power of 2, that's 4, and this is 5, 6, and 7. Right? So that's what we write it as, okay, in binary. And the result we finally get would be in this form. This will be replaced by the k value 0 itself, okay, and this will be replaced by 0, 0, 1. So we interchange the most and the least significant bits. Okay, so that's what was 1 becomes 4 here. Okay, and then what is 0, what is 2 will become 2 again. So 0, 1, 0, and this will now go to 0, 1, 1. So that's why it's 6. Okay, so what was 3 will now become 6. Okay, now this goes to 1, 0, 0. Right, so that is we had here as 4. Okay, now that became 1. So 4 becomes 1. Okay, and then this will again remain as 1, 0, 1 because it's symmetric. Okay, now this becomes 1, 1, 0, and this will become 1, 1, 1. Okay, so we had here to start with 0, 1, 2, 3, 4, 5, 6, and 7, and the Fourier transform order will be again 0, right? And now this is 4, and this is 2, and this is 6, and that is 1, and this is 5, right? And this is 3, and that is 7. So that's the order in which it will come. So it's not difficult to decipher what it is. So it will come as the Fourier transform. Okay, if you pack the array with the functions in this form, in this given as f0, 1, 2, 3, 4, etc. Those functions by this algorithm which we just looked at, the Turn-Tokay algorithm, if you use that, okay, those functions would be that array elements will be replaced by the Fourier transform, but for k values corresponding to 0, 4, 2, 6, 1, 5, 3, and 7. Okay, so that's what you will get. So that's one point which you have to keep in mind. That first point is that we need a 2 to the power of n points to implement this algorithm, and the second is that the array elements of the function value, the array elements now replaced by its Fourier transform, but in this order 0, 4, 2, 6, 1, 5, 3, and 7. That is obtained by reversing the bit, interchanging the most and the least significant bits in the in this order. Okay, that's what we will see now. Okay, we will see an implementation of how we implement such a algorithm in a program is what we are going to see now. Okay, so now this is a little more complicated than the discrete Fourier transform, okay, for obvious reasons, but much faster. And once we have implemented it, it's of course is much more easy to execute. Okay, so let's see this. Now we have the same thing, that we have the function values evaluated here. Okay, now one more problem with this thing is again that these w's here which I have written, okay, remember they are complex numbers. Okay, so when I say w to the power 1, 2, etc., these are complex numbers. Okay, so since languages like C does not handle complex numbers, we have to handle the real and imaginary part of each of them separately. Okay, for each of these functions we have to have real and imaginary part handled separately. So I do that with starting from here itself. So this function has a real and imaginary part. In principle, even the input data could be a complex number. So we say this has a real and imaginary part. Okay, and that is what I am going to call fr and fi. So my array fr and fi actually handles that real and imaginary part of the function. Okay. We are again doing an 8-point fast Fourier transform. Okay, so our input is in this particular case is real, so I am only reading out fr. Fi is put equal to 0 because it's a real function. So that's what the input value is. Okay, so now once we have the function value, I just print that out here. Not necessary actually, so we can remove this even. And then we have, now the question is how many steps do we have to go? So I said that we have to go in the steps, right? So till we reach step, everything is only one function. Okay, as the number of divisions is equal to the number of points which we have. Okay, so in this case we had 8, and at the end the number of divisions should be 8. Okay, so that's what we have to do. So we have gone from 2 to 4 to 8. Okay, that's what we will do. So that many steps we have to do. So in this case it's 3 steps. Okay, so once we know that the n can be written as 2 to the power of some m, okay, and that's the number of steps which we have to go. So that we have to compute this m. Okay, that's the first step. So first step, if you are given n, we need to compute what the number of steps we have to go, and that's given by log m by log 2. Right? So that will be, in this case it will be 3. So in general it will be log m by log 2 because we have to write our n as 2 to the power of m. Okay, so I have to start with, I have said that m is, I have introduced a new integer m and I put m equal to n. Okay, and then I compute the number of steps which are required. With this case L will be 3, remember that. Okay, and that means I have to go through 3 steps. So this is a loop. This loop here, this particular loop here is the one which would do that. Okay, so this loop goes L times. Okay, that means it goes through step 1, step 2 and step 3 in this case. Okay, so that is the outermost loop. Okay, so that loop is to go step 1, step 2 and step 3. Okay, so this division it will do. So in the first division, that is when k equal to 0, in the first loop we will divide m equal to, we divide m by half. Okay, remember m was n, so now we divide that into 2. Okay, so that whole full interval, so n1 tells you the number of points in that interval. Okay, in each interval how much is the number of points. Start with the whole thing was one interval, so n1 is same as m is same as n. So take a minute to notice this. So I need to divide my interval, I need to divide my whole set into several intervals, and I should have 3 such divisions in this case because there are 8 points. Right? So in the first set I have the whole thing as one interval, that is n1 is m, and then where m is n, which is 8, and then I divide that into 2. Okay, so m is m by 2. So that's what I did. So this is basically saying that I take this whole set as one unit, okay, and then I divide that into 2. Okay, now this is my n1 and this is my m. Okay, m is the number of points inside this loop. Okay, and then I have my k as 2 pi by n1. Okay, n1 is a total interval, and I know this is the smallest k possible. So now there is a reason why one writes it like 2 pi by n1, because notice that what we multiply here is w to the power 0, w to the power 1 and w to the power 2 and w to the power 3. That is in the first step. When you go from here to here, the multiplication is by 1 power 1, 2, 3. But in the next step, okay, the multiplication is by 0 and 2. Okay. So we don't want to do that, is difficult to implement in an algorithm. So what we do is we always multiply it by 0, 1, 2, etc. in all intervals, but we change the w itself. Okay. Right, the w itself we changed by dividing, multiplying this power by 2. Okay, so our omega naught in this case, the way I have written here, the omega naught is the same. It's 2 pi by n here, 2 pi by n here. So what I do is I write w to the power 1, w to the power 2, w to the power 3 in this step, okay, using omega naught as 2 pi by n. And the next step, okay, instead of writing w2, I will write w1, w to the power 1, but I change my omega naught to omega naught into 2. Okay, that is, this will become pi by n by 2. Okay, so that's what the reason why I write n1 here. So in the first step it is a full interval, okay, and in the next step when I go for k equal to 1, you can see n1 will be replaced by m value. M value was half that. Okay, so that means I will actually double my omega naught. Okay, so that serves the purpose that instead of changing the power here to 2, okay, I change the omega naught, I double the omega naught. So that's what both are saying. So now then I have to do that sum and difference, and that's what's been done here. Okay, so now what have we done? We just replace this into first the whole interval, replace into 2 halves, okay, and then I find the sum and difference here. Okay, now that's what this point we are doing. Okay, now these 2 loops are basically doing that. Okay, so how many times I should do that? Okay, that is depends on which interval you are in. Okay, now that's done here. Okay, so n1 is the size of your interval. So now this the interval to start with n1 is same as the whole n. So there's only one interval, right? Okay, so I'm just going to take the whole thing. Okay, so this loop in the first k value, this loop runs only once. Okay, j equal to 0. Okay, it will only run because n1 is the same as n, which will be then greater than n minus 1 by if you do that. Okay, so the first step, I go here and I just take the sum and the difference here. So okay, so I store f1r as the real part of function, okay, and f1i as the real part of function at I, okay, and f2r and f2i are the real part of the I plus m and the real and imaginary part of I plus m. So what am I doing? I am saying that when I go in the first step, okay, I have to do this divided into 2 and I have to take the sum. Okay, it has real and imaginary part, so that is I and this is I plus m, whereas m is the number of points in that interval, which is n by 2 to start with. And I replace the real and imaginary part of this f0 by the sum. That's what I done here, which is my g0 actually, the real and imaginary part of g0. And I take the difference between these two, multiply it by w0 and write the real and imaginary part and store it in the real and imaginary part of f4, right. So I do that here, and then in the next step when I go, okay, I have to do this twice, right, because for each interval. Okay, now next step when I go, I have to do this twice, okay, because now here I have to do it only once from here to here, but here I have to do between these two and then between these two, right. I have to take g0, g2, g1, g3 and then h0, h2 and h1, h2, h3. Okay, and that is what my j loop is doing here. Okay, so this j loop is basically doing that. It is telling you how many times you have to do it. The first time you have to do it only once because n1 is just n. Okay, so this loop will be do only for j equal to 0. But when go to the next loop, okay, next time, that is k, the next k value, okay, n1 is gone to half. Okay, so that means I have to do this twice. Okay, so this j loop will run for 2 values, j equal to 0 and j equal to 1. Okay, so that's what it will run. Okay, so that's the that is the basic idea here. So I had to do this replace, I had to do this twice in that particular case. So the j value goes then from not 0 to 1, sorry, 0 to, and then next one would be n1 would be now 4. Okay, so this j value will be 0 and 4. Okay. So that means that I will do 0 to 3 1 set, okay, and next j value is 4. So I start from 4 to 7 and another one, okay, because I have that functions here replaced by 4 will be this h0 and 7 would be h3, right, for f7 will be h3. Okay. So in the first set I do 0 to 4 and the next set I will do 0 to 4 to 7, okay, 0 to 4, 0 to 3 and 4 to 7, sorry, that's what we will be doing here, and that's what it's saying here. Okay, and saying that I should run from j value which was 0 in the second step, first j value is 0 and to m minus 1 which would be 3, and the next j value is j plus n1 which is 4. So I starts from 4 and it goes all the way to 7. Okay, so that is the sum and the difference again will replace. So now we keep doing this loop, okay, till we finish that, that is we will reach L is 3 here. So we will do it 3 loops. Okay, at the end we have the function values. Now only thing, one more thing which you note here is that when I do the difference, I do fr and fi, and fr I plus m and fr I minus m, sorry, fi of I plus m. So now I plus m is replaced by the difference, right. So now there are 2 points here, okay. So I have the real and the imaginary part, okay. So the real part has 2 contributions. One comes from the, so you have this w to the power 1, okay. Now that is written as cos minus I sine, right. So we have this w0, so remember w to the power n is nothing but e to the power of minus I 2 pi by n into n. Okay, so now that has 2 parts, that is cos of 2 pi by n into n and minus I sine of 2 pi by n into n. Okay, so when I compute this itself is a complex number, f0 and f4, f0 minus f4 is a complex number, and now that I am going to multiply by another complex number. So I had to pick up the 2 contributions to real and imaginary parts. Okay, so that's what I have done here. One comes from the real part of f1r minus f2r multiplied by the real part of w to the power n, and then the imaginary part of f1 and f2 multiplied by the imaginary part of w, that is the real part contribution, and similarly for the imaginary part, okay, and with appropriate signs. So that's a whole process. So then we can now write this function. Okay, again we have to divide this by n, okay, the number of interpoints which we use. Okay, so final values you get here at the end, okay, divided by n is the Fourier transform. Okay, and then we can compare that Fourier transform which we obtained with the Fourier transform which we obtained using the discrete function. So that is, so now that's been plotted here. Okay, so the value which if you run that, what we get is what is, so that's the value which we get. Okay, so now this is, we can see is now we have to compare this with okay, now so now let's compare with this. Okay, now you look at this and this value. Okay, here I have not written the k value, I just numbered it at 0, 1, 2, 3, 4, 5, 6, 7. So this is the order in which the Fourier transform is going to come out. Okay, and this is the real part and this is the imaginary part. Okay, and the one which I am showing here at the bottom. Okay, and this is the, again this is the real part and the imaginary part. Okay, or the first 5 k values. Okay, the first 5 k values, okay, which we can obtain using the discrete Fourier transform, and you can see that the numbers exactly match. Okay, but the order is completely different. Okay, so we have the same number, but the order is completely different. Okay, you can see the 0 is the same as 0, right? Okay, and now what's 1 is now here, what was 1 here has now gone to 0, 1, 2, 3, 4 here. Okay. So, what is 4 here is become 1 there, that is what we expect. Okay. Remember, so this what was, okay, let us look at this way. So, what is 0 here is the same as 0 there, right. Okay. Now, what is come out as 1 in the fast Fourier transform is actually 5 here, 4 here, 0, 1, 2, 3, 4, and that is what we see here. We said that what will come out as 1, the first, this 0, and what comes out as 1 is actually 4, right. In the element, the array number 1 in the of the data will be replaced by the Fourier transform corresponding to k equal to 4. Okay. And now array number 2, the array element 2, that is f of 2, will be replaced by Fourier transform 2. So, the discrete Fourier transform and the fast Fourier transform should match at 2. Okay, that is what we would see. Okay. So, this is the discrete Fourier transforms at k equal to 2 and matches with the fast Fourier transforms k equal to 2. Okay. So, ignore the signs here, there is something more to the signs which I will just tell you. Here right now we just look at the magnitudes, and so here we get the same matching. Okay. So, the discrete Fourier transforms 2 matches with the so the fast Fourier transforms 2 matches with that of the discrete Fourier transform. But remember the element number 1 here matches with the element number 4 in the discrete Fourier transform. So, similarly you can see other numbers also. Okay. So, they match exactly with this. Okay. So, now there is a problem with the sign. Okay. Now, that problem with the sign comes from the fact that we had this e to the power of I pi, which we did not take care in this particular Fourier transform. Okay. So, now if you have this code and in fact if you have this particular code, and then we have one more part to be written which I did not show here. Okay. That is to reorder the Fourier coefficients. Okay. So, now we have to I have one more part to this program which would actually reorder this Fourier coefficients and give us as f0, f1, f2, f3, f4, etc. So, in that order. Okay. So, we have to have an algorithm which would actually do this bit reversing and give us the correct sequence. So, that would be the end of this section. Okay. So, that is what we would want to look at here. Okay. So, now we could actually add one more part to this, and that is what we will see next, that is how to actually reorder this coefficients such that we get the same order as the function value which has been put in. So, to get the Fourier transform into this of this array of functions in the correct order, we need to do a bit reversal, and that bit reversal is done in this loop, the following loop. Yeah. So, now remember the fr and fi stores the Fourier transforms, right? And we saw that in the 8-point fast Fourier transform which we had done, we had the order as 0, and then we got it as 4, and then 2, and then 6, etc. So, we want it as 0, 1, 2, 3. Okay. So, now to get that we do the following thing, that is we start with an integer j as n by 2, that is 4, right, and then we run a loop from I to n minus 2 in steps of 1. So, whenever I is less than j, we interchange between I and j. So, there is no I am not going into the details of how this algorithm works, but algorithm is arrived at, but this algorithm works. That's so here, that is start with a j which is n by 2 always, that's it's, and then start from I equal to 1 and reverse I and j. So, the second point, the first point is 0, we do not need to change anything, that is f of 0 is same as fk equal to 0. So, and then the next one is instead of 1 it comes as n by 2. So, in our 8-point Fourier transform we got instead of 1 we got 4. Okay, so, if it is a 16-point instead of 1 we would get 8. Right? So, we need to reverse that. So, that is done here I and j are interchanged by storing first the I value into a temporary array of both real and imaginary part, and then we would flip between the I and the j values. And then we would go again, we will decrease k by n by 2, and if k, and we will run a loop till k is less than j plus 1. So remember, so we said j was 4, okay, now k is 4 here. So k is equal to k is less than j plus 1 is 5. So go here and then change j to j minus k and k to k plus half, etc. Okay, so now you do this, okay, and whenever, and you come back into this loop here, and whenever I is less than j, you flip this thing. Okay, so the 4 loops in this case. Okay, one is start from j equal to n by 2, and then we go from I going from I 1 to n minus 2, and then if I is less than j, we make a flip, okay, and then we make a k equal to n by 2, and then say that you find a new j and k value such that k is less than j plus 1. Okay, so by doing j equal to j minus k and k equal to k by 2. So you have to go through this loop till k is less than j plus 1, and then say j equal to j plus k and go back here again. Okay. So in the first case j was 4, I is 1, so you flipped j and 4, 1 and 4 came here, now k is 4, so k is less than j plus 1, so we went here. So now j is 4 and k is 4, so j becomes 0 and k became 2, right. So k is not less than j, so k is 2 here and j is 0. So we go back, come here. So now j has been put integral to 2 because k is 2 and j is 0. Okay, so we go back here, and now I is 1, but then and the j is 2. Okay, so that's what we will interchange now. Okay, so we keep doing this till we get everything reversed. Okay, so remember, to conclude, here it is start with j equal to n by 2 and run a loop from 1 to n minus 2. I less than n minus 2 in steps of 1, and reverse and interchange I and j when I is less than j. Okay. And then the next loop is starting from k equal to n minus 2, and then do this loop, that is j equal to j minus k and k equal to k by 2 till k is less than j plus 1. Okay. And then come out, put j equal to j plus k, go back and check I is less than j or not. If it is, again interchange between I and j. Okay, that's a loop. So now what we get from this is the following. If you do this, okay, and now if I plot the Fourier transform, so if I plot the Fourier transform, what we get is FFT data. Okay, so that's the Fourier transform we get. Okay, so now it comes down like this here and then goes up again here. Okay, so you see this. Okay, it comes down and then goes up again. Okay, as a number goes. Okay, now that we know that our real function was a Gaussian. Okay, so now what we are getting here, we know the Fourier transform of the Gaussian should be a Gaussian, but that's not what we get. We get it goes up like this, and that's because the way FFT works, to get the correct Fourier transform, we have to cut it at the middle, that is at the 4th point here, okay, and then paste it on the other side. Okay, so finally, what you have to do is that the Fourier transform comes in this array. This is actually folded. Okay, so if you have 8 points in the Fourier transform, and after doing the bit reversal, it comes from 0, 1, 2, 3, 4 correctly. Okay, and then the other part we have to cut. Okay, and then paste it in the other side. Okay, so that is if I can do that here. So it comes like this. So it comes. Okay, so this part comes correct. Okay, up to this, and then it's going up again here. So actually we have to make a cut here and take this part and paste it on this side. So then it will become that. Okay, so this part has to go here. Okay, that's what we see. Okay, so now that's the. So now we have seen, and this is same for the discrete Fourier transform also. So if you run the same code, same data for discrete Fourier transform, we get exactly the same results, and that also has to be cut and folded back onto the other side. Okay, so with that, we can conclude the Fourier transform part of this course.